Okay, folks, I'm going to work through a number of the problems from our in-class work to section 4.9, and we'll give this a shot. Please keep in mind that if you're watching this video, I don't think it's enough just to watch me do this, and I encourage you to struggle with these problems and struggle with them for a long time before watching me work out the solutions. That's the best way to learn. However, because we cannot meet in class at this time, I thought I'd go ahead and work through a number of these handouts with you. So please let me know if you have any questions. All right, so we're asked to find the critical numbers of this function right here. F of x is equal to x to the 2/3 power times the square root of x plus 7. So I don't think you can answer this question unless you have the definition of a critical number down. So what is the definition of a critical number? A number C is a critical number if three things. One, it's interior to the domain of f, and I guess really just two things. Either f prime of c equals 0, or what? What's the other one?
Or was undefined?
Exactly. F prime of c is undefined. Okay. But don't forget about this first part, that it's got to be interior to the domain. Okay, so let's go ahead and work through this function. Let's first state, if we want to know what the interior points are, what's its domain? What's the domain of this function? What numbers am I allowed to plug into it? Well, I'm doing some cube rooting. I'm doing some squaring, right? The 2 power gives us square. The over 3 gives us cube root. And we're doing some square rooting as well. We've got a square root there. So the domain of this function goes from -7 to infinity. So we can see that because we need x plus 7 to be greater than or equal to 0 to be able to take the square root, which means we need x to be greater than or equal to -7. And so that's how we end up with this domain right here. Okay, so we've got the domain of this function. Now let's go ahead and find its derivative. This is the hard part, and this one is actually particularly challenging. So when we go to take the derivative, notice that the major operation we have here is a product, so we're going to have to use our product rule. So here's the first, x to the 2/3, times the derivative of the second, which will be 1 over 2 times the square root of x plus 7, times 1, where that times 1 is sort of a baby chain rule, because the expression inside the square root was more complicated than just an x, so we had to do a chain rule there. But the derivative of x plus 7 is still just 1. So there's the first times the derivative of the second, plus the second, which is the square root of x plus 7, times the derivative of the first, which is 2/3 x to the -1/3. Okay. The calculus step of this, well, maybe a little challenging, doesn't get any harder than this. What's difficult is the algebra, where we try to rewrite this expression of two terms into a single fraction. So that's what I'm going to do next, and that's what's a little bit challenging with this. So let me go ahead and rewrite this as x to the 2/3 all over 2 radical x plus 7. And we're going to add to that 2 radical x plus 7 all over 3x to the 1/3. So now you can see, yep, I've got two fractions that I've got to add together. Well, how do I add together two fractions? Well, I've got to get a common denominator. So what's my common denominator going to be in this case? My common denominator is going to be 6x to the 1/3 radical x plus 7. That's the common denominator across these two denominators here. Okay. So in order to get that common denominator, let's jump up here. In order to get that common denominator, I'm going to take the first fraction, x to the 2/3 all over 2 radical x plus 7, and I'm going to multiply it by what's missing. So I'm going to multiply it by well, what's it missing? It's missing a factor of 3, because I need a 6, and it's only got a 2, so it's missing a factor of 3. and it's also missing an x to the 1/3. So I'm going to multiply this thing by 3x to the 1/3 over 3x to the 1/3. For the second fraction, we've got 2 radical x plus 7 all over 3x to the 1/3. And so what factors of the common denominator is it missing? Well, it has the 3x to the 1/3, and I need a 6x to the 1/3 radical x plus 7. So I need to multiply it by a factor of 2 and a square root of x plus 7. So let's go ahead and clean this up. When we do so, we get, let's see, I want a red pen. When we do so, we're going to get in the denominator. When we do so in the denominator, we're going to get our common denominator of 6x to the 1/3 square root of x plus 7. And in the numerator, let's see here, when I multiply the first two factors together, I'm going to get 3x to the 2/3 times x to the 1/3. So folks, I have 3 times x to the 2/3 times x to the 1/3, but that's equal to 3x to the 2/3 plus 1/3, which is 3x to the 3/3, which is just 3x, exactly. So we end up with our numerator of just 3x there. Okay. Then for the second one, I'm going to I'm going to multiply this expression together. We've got 4 times x plus 7. So I'm almost ready to clean this up now. When I distribute this 4 to both terms, we'd end up with a 4x plus the original 3x, which is 7x, plus 28, all over 6x to the 1/3 times the square root of x plus 7. All right, whew, that was some algebra. Let me give you a chance to look that over and get caught up, and then we'll resume. At this point, we can go ahead and give the domain of f prime. What's the domain of f prime? Well, there's still sort of the same operations that we had before, except that the square root operation, that radical x plus 7, is now where? Well, now it's in the denominator. So now we have to add into the fact that we can't divide by 0. And so the domain of the derivative is going to be from negative, it's still going to be -7 to infinity, but it's going to be a parentheses there. -7 to infinity. So now we're ready to identify the critical numbers. What are the critical numbers of this function? Okay. And by the way, this is a little bit confusing. It's the critical numbers of f. Okay. But when I ask you for the critical numbers of f, I'm looking at f's derivative. So I'm not asking for the critical numbers of f prime. I'm asking for the critical numbers of f. But we're going to do so by looking at f's derivative. And what are the critical numbers then? The critical numbers are x equals... Okay.
-4 and 0?
-4 is one of them. Why is -4 one of the critical numbers? Because it's where the derivative is 0, right? Great. What's another critical number? Somebody else. Or, well, actually, Steve said it. So what's another one? It's 0. Yeah. So we've got 0 is another one. Why? Because 0
it's undefined.
Because 0 is a place where the derivative is undefined. Now, the derivative is also undefined for -25. I can't plug a -25 into the derivative function. But that's not really concerning, because I couldn't plug -25 into the original function either. Now, there's one number that you might think is a critical number, and what is that?
-7.
We might think that -7 is a critical number, but it's not. How come? Because it was a boundary point in the... It was an endpoint and not an interior point to begin with. So these are the only critical numbers of this function. The question is where? How do we know that -4 is a critical number? So we ask, where is f prime of x equal to 0? So that happens when this entire expression...
I see. You set the numerator equal to 0.
Bingo. Bingo. Where is this whole expression equal to 0? And as Jackson just said, that happens when is a fraction 0? When its numerator is 0. And then if I solve that numerator for x, we end up with x is equal to -4. Great. Yeah, other questions? So the question was politely posed, is there a reason why we didn't exclude 0 from the domain of f prime? And the answer is no, there's not a reason why we did that. I made a mistake. So let's go ahead and clean that up. That should go from -7 to 0, unioned with 0 to infinity. Good catch there, Holly. Appreciate that. Okay, so let's look at number 2 here, where we're asked to find the critical numbers of this function on this specific interval. So first of all, what's the domain of the function f? Well, the domain of our function f is still -infinity to infinity. Careful here that x to the 2/3, remember, means to square the value and then take the cube root of the value. And I can square any number and I can take the cube root of any number. So that's why this domain is all real numbers. So there's the domain. So now we're going to go looking for the critical numbers of this function. And the critical numbers are where the first derivative of this function is either 0 or undefined. So let's go ahead and calculate f prime of x. So f prime of x by the product rule is x to the 2/3 times the derivative of the second, which is 2, plus the second, 2x minus 6, times the derivative of the first, which is 2/3 x to the -1/3. So now all we need to do is to rewrite these two terms as a single fraction to figure out where the fraction is either 0 or undefined. So I can rewrite this as 2x to the 2/3 plus 2 times 2x minus 6 all over 3x to the 1/3, where what I did was I rewrote this expression right here. I brought it below the line and changed the sign on that exponent. Okay, so now we can see, yep, I've indeed got two terms, and I'd like to add them together as a single fraction. So what's my common denominator going to be? My common denominator is going to be 3x to the 1/3. So this first term doesn't have the common denominator, so what do I need to do? I need to multiply it by 3x to the 1/3 all over 3x to the 1/3 to get that common denominator. Plus, and then the second term is good to go. I'm going to go ahead and in this line I'm going to distribute that 2 through, so it gives us 4x minus 12 all over the 3x to the 1/3. And now I'm ready to continue adding these two fractions together. In the numerator, notice when I multiply 2 times 3, that gives me 6. And when I multiply the x to the 2/3 times x to the 1/3, that gives me x to the 3/3, which is the same thing as x to the 1, or just x, all over our common denominator of 3x to the 1/3. And we're adding this to 4x minus 12 all over 3x to the 1/3. So that gives us 10x minus 12 all over 3x to the 1/3. So what now? Well, now we need to go ahead and find our critical numbers. Well, the critical numbers are the interior points in the domain of f such that f's derivative is either 0 or undefined. Well, if I set f prime of x equal to 0, that happens when this entire derivative expression is equal to 0, but that happens when the fraction, the numerator of that fraction is equal to 0. So that happens when 10x minus 12 equals 0, or when x is equal to 6/5. We might be tempted to say then that x equals 6/5 is a critical number of this, but it's not. How come? If I go look at the original interval, it goes from -1 to 1, and 6/5 is a number to the right of 1 on the number line. Oops. To the right of 1 on the number line, and so I'm not going to include 6/5 as a critical number. But what is a critical number? Well, there is a critical number where f prime of x is undefined, and that happens at x equals 0, and notice that x equals 0 is an interior point in the domain of this function. So that is my only critical number to this function. Okay. The next thing I ask you to do is I ask you to review number 52 in your notes. And the reason why we do that is so we can then remind ourselves, how do we find the global extremum for a function? So the first thing I say to do is to, 1, confirm that the extreme value theorem applies. We're about to go looking for our global maximum and our global minimum, and we're going to do so by a process of elimination. But for a process of elimination to work, we have to know that an answer exists. So the extreme value theorem says that we will have a global maximum and a global minimum for this function if f is continuous on the interval that we're considering, and our function is continuous from -1 to 1. And in fact, it's continuous from -infinity to infinity, so it's certainly continuous from -1 to 1. Then the interval from -1 to 1, what do we know about this, is it's a closed interval. So because the function's continuous and the interval is closed, we know f must achieve its global max and global min. So it actually makes sense to do this procedure. The next part of the procedure is to find the critical numbers of f. Well, from question number 2 above that we just worked, we saw that the critical numbers of f were at x equals 0 was that only critical number. The next thing I'm going to do is I'm going to evaluate the critical numbers and the endpoints in the function. So this is that process of elimination. F must have a global max and a global min, and they must occur either at the critical numbers or at the endpoints. So I'm going to plug both of these, or all three of these numbers into the original function. Careful, why am I checking f of x, or excuse me, why am I evaluating the function at x equals 0? I'm doing that because 0 was a critical number of f. Why am I plugging in 1 and -1 into this function? I'm doing that because these were endpoints of f, and I need to check both the critical numbers and the endpoints when I'm going searching for the absolute maximum and absolute minimum. So what is f of 0? Well, we could just go ahead and evaluate that pretty straightforwardly. We'd have 0 in this expression for x, making the entire expression 0. If I plug in a 1 into this function, we would have 1 to the 2/3 power times 2 times 1 minus 6. And if we do that, we end up with, let's see, that would be 1 times 2 minus 6, and that equals -4. And if we plug in -1 to this function, we'd have -1 to the 2/3 times 2 times -1 minus 6. Now be careful with this as you evaluate this expression. -1 to the 2/3 power, I'm going to go ahead and first square -1. -1 squared is +1. And then take the cube root of +1, and what do I get? I get 1 minus 2 minus 6, so I get -8 for this value. So that's evaluating the two endpoints. So now we can give our final statement about this problem, where we're looking for the global extremum. We say that as long as we know the global extremum exists on a closed bounded interval, they could either happen at the endpoints or at places where the function could potentially have a local max or local min, which is where we have critical numbers to the function. So we plug the critical numbers into the function, and we plug the endpoints into the function, and those were my only candidates for where we could potentially have global maxes and global mins. So x equals 0 is a global max of f on the interval from -1 to 1. And x equals which one? Well, let's see. If we plug in a 1, it spits out -4. But if we plug in -1, it spits out -8. So x equals -8 is a global min of f on the interval from -1 to 1. And those are my global extremum to this function. Folks, you can confirm this by taking a look at the graphs of the functions in Desmos, and I highly encourage you to do so. So folks, let's go ahead and pick up with number 6 here. And this is a question we've seen before, where I give you a function and I ask you where does it attain its absolute maximum and absolute minimum. So the first thing you should ask yourself is, does the extreme value theorem apply? That is, if you're going to go looking for that needle in a haystack, you want to make sure that it exists. If you're going to go looking for absolute maximums and absolute minimums, you want to make sure that they exist. So what do we say? Well, we say f is continuous on -3 to 2, so the extreme value theorem applies. That is, x is a continuous function on its domain, and that domain is a closed bounded interval. So now we go looking for our global max and global min. And to do that, there's really two things we check. We find the critical numbers and test them. And what else do we test? We test the endpoints as well. So let's go look for your critical numbers. So to find the critical numbers of the function f, what am I going to do? I'm going to take its derivative, and in this case f prime of x is equal to 5x to the fourth plus 28 x cubed plus 36 x squared, and I'm going to look for where this derivative is either 0 or where it's undefined. Well, notice that this function, in this case, is a polynomial function, and it's everywhere defined. So f prime of x is defined on its interior, or we'll just go say, well, yeah, we'll say on the interior from -3 to 2. Okay? So it's everywhere defined, but where is it 0? F prime of x equals 0. That would happen if 0 is equal to 5x to the fourth plus 28x cubed plus 36x squared. What can I do now? I can factor out an x squared. That'll leave me with 5x squared plus 28x plus 36. And then this factors. Folks, if you're rusty with factoring, please see me in a Zoom office hours and we can maybe do some factoring drills. But what I recommend doing is doing some practicing with factoring so that you're comfortable with factoring just a trinomial like this one. This factors to be 5x and x. And let's see here, this is going to be 2, and this will be 18. The signs are all positive because this tells me the signs are the same. This tells me that then both must be positive. That's positive 36. Okay. So now we've given f in f's derivative, f prime, in factored form, and so we see that the critical numbers of f prime on the interval from -3 to 2 are what? They are x equals 0, because if I plug in a 0, that factor makes the entire derivative 0. Or they are x equals -2. If I plug in -2, that'll make the whole thing 0. It will also be 0 if I plug in x equals -18/5 into this function. But why am I not concerned about that? Because -18/5 is approximately -3 points, or actually not approximately, it is -3.6, and -3.6 lies outside of our interval that we're currently considering. Okay. So those are the two critical numbers. Now I'm ready to do the answering of the question. We're going to plug in 0 into the original function, and we're going to plug in -2 into the original function. Now why am I plugging in both those numbers? I'm plugging in both those numbers because they were critical numbers of f on the interval from -3 to 2. What else am I going to plug into this function? I'm going to plug in -3, and I'm going to plug in 2 into this function. And why am I plugging in those two values? Because those were the endpoints of the interval. You've got to check both the critical numbers and the endpoints because those are the potential locations for the global maximum and global minimum. Okay. So let's see here. If I plug in 0 into this function, it's going to spit out a 0. If I plug in -2, it'll spit out, let's see here, -2, and so that spits out a -16. And if I plug in -3, it spits out 0. And if I plug in 2, let's see here, we've got 6 and 5 is 30, and we get 8 times 30, which is 240. So folks, double check my arithmetic on that, but I think we're okay. So where does f have a critical max, or where does f have a global max? F has a global max at x equals 2. Why? Because that gave me the largest y value for this function. And f has a global min at x equals -2. Why? Because that gave me the smallest y value on that interval, and that is my solution to this problem. Folks, I want to say one thing real quick. when I write these problems, I try to make them something that's easy for you to work with. And so for that reason, there's not a whole lot of potential numbers that you would plug into this function. So for example, if you were plugging in only nice numbers into this function, you might plug in -3, -2, -1, 0, 1, and 2. You might just plug in those nice numbers into this function, and then you could check your answers. Now, could you from that list maybe guess what the global max and global min is? Yes, that's correct, but you've not done the correct procedure here. So it's absolutely essential that you follow this procedure that we're doing. Otherwise, I would just give you a more difficult problem to do, in which case that method of just plugging in nice numbers certainly wouldn't work. So folks, that concludes the warm-up. I'm going to go ahead and continue some other questions here through this video. Okay, folks, now let's look at number 24 in the middle of the Growing Your Calculus Skills. And we're asked to find, careful here, this notation is important, not an antiderivative of f of x. We're asked to find the antiderivative of f of x. And so what is the antiderivative? It's capital F of x is equal to what function, when we take its derivative, will give us 3x squared? What function, when we take its derivative, will give us 3x squared? Well, the answer is x cubed is one of them, but so would be, say, x cubed plus 2, or x cubed minus 5, or x cubed plus the square root of 6. There are many functions that when I take their derivative will give me 3x squared. And what are we looking for in this problem? We're looking for the family of functions that give that as an antiderivative. So x cubed plus c is that general antiderivative. That's what we call the antiderivative. So notice I needed to have this plus c in this solution. It needs to be a family of functions and not just one function. So if you miss that plus c, you'll be docked on this problem. Okay, now we're asked to graph f of x for a few different parameters. So let's go ahead and graph f of x is equal to x cubed plus 0, which would just be x cubed. And we'll graph this function, let's call it g of x, is equal to x cubed plus 1. We'll graph that function. And h of x is equal to x cubed minus 2. So let's graph all three of these functions on the same graph system, the same coordinate system. So let's see here. Here's x, and here's y. And so for a c value of 0, we just are graphing the function x cubed. Well, that's the cubic function that looks something like that. That's what we get when c is equal to 0. And when c is equal to 1, for this second one, let me do that in a different color. For c is equal to 1, we're going to graph the function x cubed plus 1. So it has a y-intercept of 1, but other than that, the shape of this curve is identical to the other one. And what's important to notice here is, could this green curve ever intersect this blue curve? Well, no, because they're the exact same shape. One is just shifted up 1 unit from the origin, while the other one is at the origin. So those two functions are identical, with the exception of one being a translation of the other, or one is shifted up from the other. Other than that, their shapes are identical. Let's go ahead and graph the third one when c is equal to negative 2. That's this function right here, x cubed minus 2. And let's see here, to plot that, we could go ahead and drop down 2 from the original point of 0, 0, and we can go ahead and sketch the graph. This is when c is equal to minus 2. And I think I forgot to label this. This first one was when c is equal to 1. These are sometimes called level curves of this function. Notice that I've selected different constants for my arbitrary constant c, but in all cases, this function has the exact same shape. Why is that? Well, because for it to have the exact same shape, it has to have the same rate of change. Any one of these has to have the same rate of change, and they all do. They all have the same derivative of 3x squared. So the second question, or actually part C here, asks us what are some properties we notice about these curves of f of x. Okay, so this is something that I just said in the previous example. One, notice that they all have the same shape. Okay? And that one way to say that, or one way to realize that they all have the same shape, is that they all have the same rate of change. What do I mean by the rate of change? I mean they all have the same derivative. The derivative of all of these, f prime of x, is our given f of x, which is just 3x squared. They all have the same derivative. Okay? So notice that because they all have the same shape, but they all have different y-intercepts, then these curves will never intersect. And that's probably the biggest takeaway point from this example. These curves will never intersect. So this next problem asks us to find capital F of x so that f of 1 is equal to 9. Well, if f of 1 is equal to 9, that's the same thing as saying that this curve must pass through the ordered pair 1, 9. So let's look at these. We drew these curves here. Does any one of them pass through the ordered pair 1, 9? Well, let's see here. I don't think so. If I were to plug 1 into this first one, x cubed, if I plug in 1, it just spits out a 1. If I plug in a 1 into this second one, it would spit out 1 cubed plus 1, or it would spit out 2. And if I plug in 1 into this third one, it would spit out 1 cubed minus 2, or negative 1. So that is, this goes through the ordered pair 1 minus 1, this goes through the ordered pair 1, 1, and this goes through the ordered pair, it's kind of hard to see here, the graph's getting a little cluttered, but that group goes through the ordered pair 1, 2. Okay? So none of those are the curves, even though they've got the same shape. So what did we say about our function? We said our function, capital F of x, is x cubed plus c. So what do we not know? We don't know what that arbitrary constant is, c. So we need to solve for that c. And the way we do that is we replace the functional value with 9, and we replace the x value with the domain input of 1. And so we get that 9 must equal 1 cubed minus c. Plus c. I dropped that plus sign. Plus c. And so we end up with c must equal 8. So what is our answer? Our answer for this particular solution curve is x cubed plus 8. That's what we mean when we say we want to find the particular solution from this family of solutions so that we satisfy this given condition. Okay? So in general, when you go to find the antiderivative of a function, you're going to have an entire family of functions, some of which I've drawn in this graph here. Okay? But sometimes we want to specify which member of that family of functions do we want, and for us to be able to figure that out, we have to be given one particular point of interest. Okay? So we call this an initial condition, or some other condition for this function, and from that we're able to solve for that constant. Now it's not a family of curves, so it's certainly a family of curves all of which have the derivative of 3x squared, but it's only one of those curves that has the derivative 3x squared and passes through the ordered pair 1, 9. Because if these curves never intersect, which is what we said, that was the big conclusion from C, then only one of them can pass through the ordered pair 1, 9, and this is the one that does that. Okay? So folks, I went ahead and worked number 25. The first thing I did was I just rewrote the derivative expression to make it a little bit easier to read. Sometimes people have a hard time reading that expression, 3x over 2. That's just 3 halves x, right, or minus 3 halves x in this case. So I just rewrote the derivative, and then from here to here, from this line to this line, I took the antiderivative of this function. So I asked myself, which functions when I take the derivative give me e to the x? The answer is e to the x. What function when I take its derivative gives me the secant of x tangent of x? And the answer is the secant of x. And then I said, what function when I take its derivative gives me minus 3 halves x? And the answer is minus 3/4 x to the second. Now you might have a little bit of trouble with that one, but remember you can use your power rule for antidifferentiation, which says that if f of x is equal to x to the n, its antiderivative is equal to 1 over n plus 1, x to the n plus 1, and this holds for n not equal to negative 1. So that's the power rule that I used to calculate this antiderivative. If you have questions on that, please see me. Okay? Now, at this point, what have I done? I've given the antiderivative as a family of functions. Okay? Any function for any choice of constant c here, when I take its derivative, will give me the blue function f prime of x. But I don't want just any of them. I want the specific one amongst them that satisfies this condition here, that when you plug in a 0, it spits out an 8. So to figure out which one I went ahead and plugged in a 0, outputs an 8, so we set this family of functions equal to 8, replacing the x's in that expression with 0, and then we solve for the corresponding c value that will make that true. Now that we've done all that, we can go ahead and give the answer. This is the answer to the problem. Careful, the answer to the problem isn't just what c is. The answer to the problem is the specific function. F of x equals e to the x plus the secant of x minus 3/4 x squared plus 6. That's what we found the answer to be in this problem. Okay. So now let's go ahead and answer number 26 together. So in this case, folks, for number 26, it's a little bit different than we've seen before. We're given this, what the second derivative of the function should come out to be, and we're asked to find the original function. So although it's a new question, it's really just the same procedure we've been doing. We're just going to have to find two successive antiderivatives of f double prime. If we find one antiderivative of f double prime, that will lead us to a family of functions for f prime. And if we find the antiderivative of that, it will lead us to another family of functions for f. So we're going to have to antidifferentiate twice here. So we would find out that f prime of x is equal to 4x to the third plus 3x squared minus 4x plus c. Normally I just write plus c. In this case I'm going to write plus c1 here because you're going to see I might have multiple constants in this problem. Okay. So folks, if I did that a little bit fast because we're just getting used to this, I'm doing the antiderivative power rule. So I'm doing the power rule for antidifferentiation here that says, for instance, to evaluate the antiderivative of this power function, I'm going to add 1 to the exponent, making it 3, and then divide by the new exponent. So I took 12 divided by 3, and that's what gave me 4. Okay. So that got us to the family of functions that represents f prime of x. Now let's go ahead and give the family of functions that represents just f of x by taking the antiderivative of our most recent answer. So if I take the antiderivative of f prime, I'm left with x to the fourth plus x cubed minus 2x squared plus, careful, how do I do this? Well, when I take the antiderivative of c1, or any constant, what am I left with? The antiderivative of a constant function is a linear function. And double check this. Take the derivative of c1 times x, what do you get? You just get c1. So yep, we're on the right track. Now, again, I'm looking for a family of functions, so I need a plus c2 there, because this c2 comes from when I took the antiderivative of second time. Okay. So now we've given the antiderivative. This is the antiderivative of f prime, but we specifically want this function to satisfy these two conditions here. That is, when I plug in a 0, I want it to output a 4. Well, that would mean that 4 would be equal to 0 to the fourth plus 0 to the third minus 2 times 0 squared plus c1 times 0 plus c2. So that would mean that c2 is equal to 4. Okay. So we know what c2 is. Now let's go ahead and see, let's see here. Well, we could restate f of x now as x to the fourth plus x cubed minus 2x squared plus c1x plus, instead of c2, I've learned that that needs to be 4. Okay. But now we need to figure out what c1 of x is. Well, luckily we've been given another initial condition, and so we can go ahead and find out what c1 needs to be. I know that if I plug in a 1, it needs to output a 1, so that tells me that this statement needs to hold. that 1 on the left-hand side needs to equal 1 to the 4th plus 1 to the 3rd minus 2 times 1 squared plus c1 times 1 plus 4, or if you clean this whole thing up, we end up with 1 is equal to, let's see here, that's 1 plus 1 minus 2, which is 0, plus 4, so 4 plus c1, or that c1 is equal to negative 3. So finally we can give our answer as the function f of x is equal to x to the 4th plus x cubed minus 2x squared minus 3x plus 4, and there is our solution. This is the function that when I take its derivative twice will give me 12x squared plus 6x minus 4, and if I plug in a 0 to it, it spits out a 4, and if I plug in a 1 into it, it spits out 1. Folks, let me know if you have any questions over this, and we'll continue on in a moment. So folks, in number 27 here, we have the exact same function, but the way we were given the initial conditions is slightly different, and so I've gone ahead and worked that through for you, and I'll let you take a look at it. The only difference between the two is really that when I go ahead and find out what f prime of x is by taking a first antiderivative, I'm able to solve for that unknown constant c1 in the first derivative because I was given a statement about the first derivative there. So I go ahead and plug in the order pair 0 for x and 7 for f prime of x, and I'm able to solve for that first constant. And so before I even go trying to find the original function, I'm back to a function without any constants in it. Then I went ahead and took the antiderivative of that answer and got an expression with a c2 in it. Then I can use this second initial condition to help me solve for c2. And this is what we end up with as a final answer. So pause the video, take some time, and see if that makes sense. Okay, folks, so let's look at this next question, and this is a physics question where we're given an acceleration of a particle. So if you remember back when we first did these motion questions, I gave you the position function and then would sometimes ask you to come up with either the velocity function or the acceleration function. In this case, we're working the problem differently, where I'm giving you the acceleration function and you're asked to come up with the position or the displacement function. So let's see what we can do here. We're told that a of t in this problem, that a of t, let me grab a different pen, that a of t is equal to 6t plus 4. Well, we know that the derivative of the velocity is the acceleration, so the antiderivative of the acceleration function then is the velocity function. So we end up with v of t then would be what? Well, if I take the antiderivative of 6t, I end up with 3t squared plus 4t plus some unknown constant, c. But I was told that the initial velocity is negative 6 centimeters per second. That is, when t is 0, this is traveling at negative 6 centimeters per second. So we end up with negative 6 equals 3 times 0 squared plus 4 times 0 plus c. And so we find that c would have to equal negative 6. By the way, you might be starting to see a pattern for initial conditions. If it's a polynomial and the condition has to do with when time is 0 or when x is 0, then it's very easy to solve for that c value. So we now know that our velocity function in its entirety is v of t equals 3t squared plus 4t minus 6. That's our velocity function. But we're asked to find the displacement function, so what do we need to do? We need to go ahead and take the antiderivative of the velocity function. Remember, if the derivative of the displacement function is the velocity function, then flipping that around, the antiderivative of the velocity function is the displacement function. And so we get that s of t would be equal to t cubed plus 2t squared minus 6t plus some other constant. And here we were told that our initial displacement was 6 centimeters to the right, so we know that s of 0, excuse me, I said 6, I meant 9, s of 0 is equal to 9, and so we end up with 9 is equal to 0 cubed plus 2 times 0 squared minus 6 times 0 plus c1, or that c1 is equal to 9. So at long last, we're able to give our solution to this problem. What's our solution? Our solution is that s of t is equal to t cubed plus 2t squared minus 6t plus 9. That is the specific position function that when you find its acceleration, you would find that's its acceleration, and initially it's got a displacement of 9 centimeters to the right, and initially it's got a velocity of negative 6 centimeters per second. So this is the one function that does that. And so resume. All right. The first thing I want to say is that this is let me get these photos out of the way. This is a really kind of a nice capstone question to where we are at calculus at this point. If you read through this question, I don't give you a lot of details, and I'm not giving you a mathematical function. Instead, I'm just giving you some nice initial conditions that you could probably obtain through scientific instruments. So I'm telling you what the initial speed, the initial velocity actually, of this ball is. It's going at 48 feet per second upwards, off of a cliff that's 288 feet above the ground level. And then I'm giving you a fact that if you've had any physics classes, you've seen in a physics class, that is the acceleration due to gravity on planet Earth, which is essentially constant. Okay? That's all the information I'm telling you. I'm telling you that a of t is equal to negative 32 feet per second squared. I'm telling you that when you get your initial velocity, that it's 48 feet per second. And I'm telling you what your initial height is. Your initial height is 288 feet. What I think is pretty impressive is how, using only the tools of calculus, we can take these three facts, which is all they really are, and we can completely describe the motion of this ball. Okay? Technically, I'm lying slightly. We're not going to incorporate wind resistance, etc. But this model for the path of this ball will be highly accurate, and you could test it. You could test it experimentally and see how good of a job this model does at modeling what happens when a ball leaves a cliff of 288 feet at this particular initial velocity. We've done problems like this before. We did this problem. We did a similar problem for our applications once we learned the derivative. But in that problem, I had to give you the function. I said, this function describes how the ball moves. And that's not very realistic. In the real world, somebody doesn't come up to you and tell you what the function is. So we're starting this problem from three facts. And from these three facts, we will arrive at a very cool physical equation describing the motion of the ball. So let's go ahead and do this. We know what a of t is. A of t is negative 32. Well, we want to go ahead and find the position function for this ball and the velocity function. Well, what do we know about the acceleration function? It is the what of the velocity function? So the derivative of the velocity function is the acceleration function. So what is the antiderivative of an acceleration function? It's velocity function. So to find the velocity function, I'm going to take the antiderivative of my acceleration function. And what is the antiderivative of the acceleration function? It would be just minus 32t, and normally what I'd write is plus c. And if you want to write plus c, that's just fine. But when you encounter this equation in a physics class, they will actually put plus v naught. V naught standing for the original velocity. And in fact, at this point, we know that v of 0 equals 48. So that means that 48 has to equal negative 32 times 0 plus v naught. And we see, okay, yep, the initial velocity is at 48 feet per second. So now I can go ahead and give the velocity function in full detail as minus 32t plus 48. And if you've had a physics class, this was the equation you were given for a velocity. I think it's pretty cool. We're not being given those equations. We're deriving them from physical facts, which is pretty cool. we can actually now ask the question, when does the ball reach the maximum height? Because how would we figure out when a ball reaches its maximum height? How would we figure that out?
When the instantaneous velocity is 0.
Bingo. When the instantaneous velocity is 0. So what am I going to do? I'm going to set v of t equal to 0, which happens when minus 32t plus 48 equals 0, which happens when t is equal to minus 48 over minus 32, which happens at positive 1.5 seconds. Folks, I think that's really impressive, right?
Can you leave that for just a second?
Yeah. Folks, I think that's really impressive. Being given just these initial conditions, which is something that you could just measure. What's the acceleration of gravity on Earth? Well, that's a fact. It's negative 32. You could verify that experimentally. But then knowing what your initial velocity is and knowing what your initial height is, we can now say what the when this ball achieves its maximum height. We know that it's going to start falling back to Earth after 1.5 seconds have passed. Okay. Let's continue with this. We found the velocity function by taking the antiderivative of the acceleration function. So if I want to find my position function, what can I do? My position function is going to be what? The antiderivative of my velocity function. So that's going to be the antiderivative of negative 32t plus 48 taken with respect to time, dt. So let's actually evaluate that antiderivative. We get negative 16t squared plus 48t plus, and I'm going to go ahead and put an s naught here. That s naught stands for the initial height. Since s of 0 equals 288, we get that s of t, our final statement for s of t, is that s of t is equal to minus 16t squared plus 48t plus 288. And this is the equation that completely describes the height of the ball at any point in time. And again, I find it fairly impressive that given just this little bit of information at the beginning, we were able to come up with a function that described the parabolic height pattern for this ball as it flies off into the air, rises up to its apex, and then begins to fall back to Earth. All with just calculus. We don't have formulas like you do in a physics class that we have to memorize. We can just start from basic facts and build the formulas ourselves. Okay. To finally answer the question, the second question is, when does the ball hit the ground? So I'm going to answer that question, I'll set s of t equal to 0. That happens when minus 16t squared plus 48t plus 288 equals 0. And then I just need to solve this quadratic equation. I'll do this really quickly, then I'll pause it and see if you have questions, but I'll give you more time here with it in just a second. Factoring out a negative 16. That happens when t equals 6 or t equals negative 3. We throw out the negative answer because that's not in the domain of our problem. And so at t equals 6 seconds, the ball hits the Earth. And again, I think that's fairly impressive that given this little information, we can answer some really interesting physical questions. And so that's kind of a nice little capstone for calculus at this point. So folks, let's look at number 32, the last question on here, and it's here that we introduce some new notation. Really, it's just new notation. There's no new concept here. It's just rather than writing capital F of x as the antiderivative of an expression, we're going to write the antiderivative of little f of x. So, for example, we would write that the antiderivative of the cosine of x dx is equal to what? Well, the answer is the sine of x plus c. Why? Because any one of these functions in this family of functions, when I take its derivative, will give me back to the integrand, the expression inside the integral there, which is what we wanted to come up with. Okay. So make sure you practice this vocabulary. That's what I have you go through here. I think all the answers are there in the line above it. But let's go ahead and evaluate the following indefinite integrals. So if we evaluate this one, we can evaluate the antiderivative termwise. And so we would end up with x to the 6th plus 7/2 x squared plus the natural log of the absolute value of x plus c. Be very careful. Remember, I don't use the power rule on the function 1 over x. The power rule doesn't apply to the function 1 over x. Instead, I just say, well, what function when I took its derivative gave me 1 over x? And for the positive numbers, that was the natural log of x. But to give the entire function over the entire domain of 1 over x, we would use the natural log of the absolute value of x. That's the antiderivative of this function. This problem here says to give the antiderivative of secant squared plus 7e to the x. Well, that's going to be the tangent of x plus 7e to the x plus c. Why? Because the derivative of the tangent is secant squared. The derivative of 7e to the x is 7e to the x. And the derivative of constant zeroes out. Okay. So folks, it's exceptionally important that you work through number 3 here. I give you all the information you need. So I'm going to let you go ahead and do that. So folks, here we have the answer to number 3. Do make sure you work through that. That's a very common test question for me to ask. So make sure you understand all of those steps. For number 4, the antiderivative of this function would be the arctangent of x plus c. Why? Because what's the derivative of the arctangent of x? The derivative of the arctangent of x is 1 over 1 plus x squared. So that means that the antiderivative of 1 over 1 plus x squared dx is the arctan of x plus c. Okay. So let's look at number 5. What are we going to do there? Well, we're just going to do some clever rearranging of things. Notice I can rewrite this integral as the integral of 4 cosine x all over the sine of x times all over the sine squared of x plus the sine squared of x all over the sine squared of x. So I just broke this up into 2 fractions, dx. And this first expression here I could rewrite as 4 times 1 over the sine of x times the cosine of x all over the sine of x. And the second expression I could rewrite as 1. So folks, do double check, make sure that this makes sense to you. If you don't believe me, go ahead and multiply out your numerators. You'll have 4 cosine x. Multiply out your denominators, you'd have sine squared of x. So that's how we could rewrite this problem. Why am I doing it that way? Because I'm trying to put it in terms of my elementary antiderivative rules. So I can now go ahead and rewrite this as the integral of 4. What's another way of writing the sine? Well, 1 over the sine of x. We could write that as the cosecant of x. And what's another way of writing the cosine of x over the sine of x? We can write that as the cotangent of x plus 1 dx. And now, and only now, am I ready to evaluate this antiderivative. Okay? By the way, I should now put parentheses inside my integrand. That's a good habit to get into, so that the integrand should be in parentheses there, and in parentheses there. You don't have to do that, but it's a good habit to get into that. Okay, so what function, when I take its derivative, gives me 4 cosecant x cotangent x? Well, that is 4 times the minus 4 times the cosecant of x. Remember, the derivative of the cosecant of x is equal to minus cosecant x times the cotangent x. And so if I ask you what's the antiderivative of 4 cosecant x cotangent x, the answer is minus 4 cosecant x. Plus, what's the antiderivative of 1? What's the antiderivative of 1? It is just x and then plus c. Do not forget your plus c on that answer. So folks, there's a quick, well, I don't know how quick it was, an hour-long video over our in-class work. Please take a look at that and let me know if you have any questions.